Hello students, welcome you all once again in the online platform of Sharda Vidya Mandir. Today we are going to start a new chapter. The name is complex number. Do you remember in your earlier classes you have learnt about the real number system? There you have learnt about the different parts of real numbers. First you have learnt about the natural numbers, and then you have included the zero with it and you have named it whole numbers. Then you have added all the negative of the natural numbers into it and you named it integers. After that you have zoomed into the number line and found so many other fractions are there between two consecutive integers, and you have included them all in your number line and you have named it rational number. Also you have observed that many other numbers are there. In spite of being a real number, they don't have the terminating or recurring decimal expansion, so you have named it irrationals and you have grabbed all of them inside your bag of real numbers. That is your complete bag of real numbers. And now we are interested to find what is there beyond this bag of real numbers and where do we actually need them. And if they don't have any place in the real number line, then where do they actually lies? The answer is, if we want to go beyond the real number line, we will actually fall into the two dimension, which is nothing but a plane, and we often call it a complex plane, which is same as your Cartesian plane that you have learnt in the coordinate geometry. As you know, there should have two axes in the Cartesian plane, so it also has the same, which is known as real axis and imaginary axis. And also all the points in this plane are known as the complex numbers. Therefore, you might have observed that our old well-known real number line is lying at the middle of this plane. So it is definitely can be brought to the conclusion that real numbers are the part of a complex number. Now the next question is, why the complex numbers were needed to be introduced? Because we were stuck when we came to solve an equation like x square plus 1 equals to 0 or any other quadratic equations where the discriminant is less than 0, because we didn't have any idea about the square root of a negative number. So we have introduced the square root of minus 1 as I, the small letter I. I stands for imaginary number here. So if we have to express any negative number within the square root, like root over minus 169, so then we just do root over minus 169 is equals to root over minus 1 into root over 169, which is nothing but 13i, because root over 169 we know that is 13, and root over minus 1 is I. We have introduced that. Therefore, square root of any negative real number is known as the imaginary number, and they don't exist in our reality. It is only in our imagination and it's completely abstract. Now, together a real part and an imaginary part, it is known as a complex number, like 5 plus 3i, 2 minus root 3i. And these are the examples of complex number, and it is also denoted by open interval a comma b, like a coordinate of a point where both a and b are real numbers, but a is measured along the real axis and b is measured along the imaginary axis. Now the next segment is algebra of complex number. First it comes addition of two complex numbers, where addition of the two complex number is very easy. Just you have to add the real part and imaginary part separately with each other. Now few properties are there under the addition of two complex number. First one is, if we add two complex number, we will always get a complex number in result. That is, the complex number is closed under addition. And next is commutative property. If we add two complex numbers z1 and z2, or if we add z2 plus z1, they both are same basically. And complex number is also associative. That is, three complex numbers z1 plus z2 plus z3, there if I add the first two at the first or if I add the last two at the first, it doesn't matter, the answer will be same. And there exists the additive identity in the set of complex numbers, that is 0. As we know, 0 can be expressed as a complex number, that is 0 plus I into 0. Now we know that any number which can be expressed in the form of a plus ib, that is a complex number. So 0 is also can be expressed as 0 plus I into 0. So 0 is also a complex number, and that exists in the set of complex numbers. So additive identity exists in complex number. Also, we have additive inverse to every complex number in the set of complex number. That is, if I choose a complex number a plus ib, the additive inverse of that complex number will be minus a minus ib, where this minus a minus ib is denoted by minus z if a plus ib is denoted as z. So that z plus that minus z will be the additive identity, that is 0. For the difference of two complex number is also the same as we have done in the addition. We will calculate the difference in the real part and imaginary part separately, and we will get another complex number as a result. One point I want to mention here, that difference of two complex number is neither commutative nor associative. So these two properties doesn't hold there. Now for the multiplication of two complex number, we will multiply them like a multiplication of two binomials. That is, if one complex number is a plus ib and another complex number is c plus id, we will multiply them like a binomial. A will be multiplied to c and a will be multiplied to id, ib will be multiplied to c and ib will be multiplied to id. So as a result, we will get ac plus I into AD plus BC plus I square into BD. Now I square, the value of I square is minus 1, as the value of I is root over minus 1, so I square is equals to minus 1. Therefore BD will come to the real part, so AC minus BD plus I into AD plus BC will be the result. And after the multiplication, we have to convert the result into a complex number, that is a plus ib format, as we have done in all the other operations, addition and subtraction. We got the result as a complex number, so in case of multiplication also we will get the result as a complex number. Now for the properties of complex number under multiplication, first of all, it is both associative and commutative. And in case of identity element, one is the identity element under the multiplication. Here one is also be treated as complex number, as one can be written in the format a plus iv, that is 1 plus I into 0. So one can be treated as complex number, and it is the multiplicative identity. Now in case of inverse, every non-zero complex number has a inverse under the multiplication. If the number is taken as a plus ib, then its multiplicative inverse will be a minus ib divided by a square plus b square, which is nothing but conjugate of the complex number z divided by the square of the modulus of z. Wait a minute, what is conjugate and what is the modulus of a complex number? We didn't have discussed this, so let's discuss that first. Conjugate means the replacement of I by minus I in the given complex number. So in a given complex number, in the place of I, if I put minus I, then the complex number will be called the conjugate complex number of the given complex number. For example, if I take the complex number to be minus 2 plus 5i, then its conjugate complex number will be minus 2 minus 5i. And if I take the complex number to be 5 minus 3i, then its conjugate complex number will be 5 plus 3i. And the modulus of a complex number is the square root of the sum of the squares of the real part and the imaginary part separately. That is, if I want to say it in simple words, then if a plus ib is a complex number, then its modulus will be root over a square plus b square. And this modulus of a complex number z is denoted by mod z and the conjugate of the complex number z is denoted by z bar. Okay, we will discuss the geometry of both the modulus and the conjugate complex number more elaborately in our next video. Now let's come back to our algebra of the complex number once again. We were discussing about the multiplicative inverse of a complex number. Next is multiplication of complex number is also distributive over the addition, that is z1 into z2 plus z3 within the first bracket is equals to z1 into z2 plus z1 into z3. Now, in case of division of two complex number, we use the concept of multiplicative inverse and we multiply the inverse of the denominator with the numerator. For example, if I have to divide a complex number 5 plus 10i by another complex number 4 plus 3i, then we will just multiply the inverse of 4 plus 3i with 5 plus 10i. Now the inverse of 4 plus 3i is 4 minus 3i divided by 5, and if we multiply them, and we will get 10 plus 5i, which is nothing but 5 into 2 plus I. Next, one more thing we will be applying to solve the problem in this chapter is power of I. We know the value of I is equals to root over minus 1, and then I square will be minus 1, and if I have to find I cube, then I will be applying I square into I, that is minus 1 into I, which is nothing but minus I. Similarly, if I have to find I to the power 4, then I will do I square then whole square, which is nothing but minus 1 whole square, which is plus 1. And similarly, we can find the other higher powers of I.